Hey, this is Dr. B, and welcome to stoichiometry. Stoichiometry is essentially the study of the mole. And the mole is simply a number, that number being 6.02 times 10 to the 23rd. It's just a number, and it's easy to measure. Let's have a look. What we'll study is what it is, which I guess I just told you. We'll use it to balance equations. We'll use it to do some conversions, for example, mole to mole, gram to mole, and like that. We'll apply it to the topic of limiting reactants, where you're randomly mixing non-stoichiometric amounts of substances and what happens. We'll use it to determine percent composition, empirical and molecular formulas, solve combustion analysis problems, and we'll do a summary. So let's go ahead and begin. The mole is just a number, and it's very easy to measure. And in order to give you a little background, rather than just tell you it's a number, let's consider a molecule of water. I've exaggerated the size of the oxygen atom a little bit to give you an idea that it's by mass mostly oxygen. In fact, here's the actual mass of an hydrogen atom, and here's the actual mass of an oxygen atom, which is much larger. The oxygen atom is 16 times more massive than a hydrogen atom. Were the atoms all the same masses, there would be really no use for the mole, because the mole is designed to adjust for the fact that some atoms are heavier than others. Let's apply this in a practical sense. Suppose we wanted to make some water. I see two hydrogen molecules, H2, and one oxygen molecule. These can combine like this. To form two water molecules. But clearly you wouldn't be mixing equal masses of hydrogen and oxygen. Balancing it, we see we need two hydrogen molecules for each one oxygen molecule in order to make two dihydrogen monoxide or water molecules. And when we do so, the mass of that one water molecule is insanely low. Look at how small that is. So, in order to compensate for these different masses, we use the mole, which is just a number. It's a number that is, let's just say for now, that it's tuned so that if you use that many atoms or molecules or anything, you'll have useful amounts. It accounts for the fact that atoms are so insanely low in mass. If you have a mole's worth of hydrogen atoms, you have a gram of hydrogen atoms. They're very light. If you took the same number of oxygen atoms, being 16 times heavier, you'll have 16 grams of oxygen atoms. I hope you're beginning to see that this is going to be useful, since you can now weigh out the proper amounts. When we scale up to molar amounts, we say that 2 moles, see that? 2 moles of hydrogen, since each one is 1 gram per mole, we'll use 2 times 2, which is 4 grams of hydrogen molecules, and we better combine them with 1 mole, see that? 1 mole of oxygen atoms, which is 32 grams, and that'll give us 36 grams of water. We now have a recipe. If we want to make 36 grams of water, no problem. Use 32 grams of oxygen, use 4 grams of hydrogen, and you're good to go. You will have the correct number of atoms, or in this case molecules, of each, and you will be adjusting for their sizes. So what can we say about 1 mole of helium, for example? We'll look it up on the periodic table, and you'll see that it can, if it's a mole, it clearly is 6 times 10 to the 23rd atoms of helium, and it'll weigh 4 grams. That's its molar mass. That means it's a little heavier than hydrogen, 4 times heavier. Interestingly, and we're getting into a slightly different subject, if you take a mole's worth of it at standard temperature and pressure, that's 1 atmosphere and 0 degrees Celsius, you'll find that it's 22.4 liters. In fact, if you take any of the gases and you use a mole's worth, you'll have 22.4 liters. The reason being that there's just so much space in between in the gaseous phase that the identity of the gas doesn't really matter. Okay, that's a little introduction to the mole. And we're talking about the subject of stoichiometry, which literally translated means element measuring.